Hey everyone. If you want to see our sample solutions to the midterm, I've got those on the web page this afternoon. Today's going to be a continuation of exceptions and some other stuff. Today's going to be the last lecture on Java. And from here on in, we go on to more interesting things. Like on Friday, I'll be talking about our first really serious, complicated algorithm, an algorithm for playing games like chess or tic-tac-toe, and that will be the basis of your project too. Next week, we'll talk a little bit more about software engineering. We'll talk about algorithm analysis. And then for the rest of the semester, we talk about data structures and algorithms and a lot of stuff that's really a big part of the theoretical core of computer science. Now today, unfortunately, I'm out of big chalk, so I apologize in advance if this turns out hard to read. Maybe I'll do it on this one. Lovely. Maybe we don't need to learn any more Java. Maybe that's it. Finally, the Java is over. A finally clause is something that can be part of a try clause and part of your exception handling routine. So when you start with a try clause, as usual, have some statements that might throw exceptions. And suppose that if everything works out normally, then this try clause will return 1. But if an exception occurs, then we'll skip over that and catch some exception instead. And one of the things I mentioned before that's interesting about exceptions is that there are a few methods you can call on them that give you information about what happened. Like, for instance, you can print a stack trace that shows what methods were executing when the exception happened. And perhaps that'll help you debug. And maybe if an exception occurs, I'll try to return 2. But now at the end, I can have a finally clause. And that looks like this. A finally clause is composed of statements that I want to happen no matter what happens. Whether an exception is thrown or not, I want to do some cleanup at the very end every time. For instance, maybe I want to close a file. Maybe this is a point at the program where whether I successfully opened and read the file or not, now it's time to close it. And so I should do that even if an exception was thrown, even if an exception was not thrown. And here I'll return 3. So the rule is, if the try statement begins executing at all, then the finally clause, or at least the beginning of it, will be executed no matter what. And so that's the golden rule to remember. Did you have a question? It'll return 3. And so that's a great question. The next thing you need to know about this is that this piece of code always returns 3. So in a way, this is a contrived example, because the return 1, well, we hit the return 1, and what does Java do? Well, Java says, okay, it's time to end this procedure, but first I have to execute the finally clause. So it executes the finally clause, and when it's done that, it would go back to whatever it was doing, but the return 3 supersedes the return 1, and so 3 is what gets returned. And likewise, if some exception gets thrown, then by statement X, then we'll jump over that return and we'll go and execute this, and then we'll try to return 2. But when Java reads return 2, it says, okay, I'm going to return 2, but first I need to execute this finally clause. So it comes down here, executes this, and again, the return 3 supersedes the return 2. So again, it's a contrived example. You wouldn't write code like that, but if you did, that's how it would work out. Yes? Oh, you can return any type you want, just as long as you declare that as the type you're returning. Other questions about this so far? So let me write down the details again. There's several things that could happen. One is that statement X causes a sum exception. And if that happens, then the catch clause is executed. And then the finally clause executes. If statement X causes an exception that is not a sum exception or a subclass of sum exception, then there's no catch statement for it. So if it causes some other type of exception, it's not a sum exception, then the finally clause executes immediately. We stop whatever we were doing in the try clause and go straight to the finally clause. And then, because that exception was never caught, it will continue to propagate down the stack. So you see the finally clause does not catch that exception. It just delays it. We execute the finally clause, and then the exception continues doing what it was doing before, breaking all the routines down the stack and maybe printing an error message if it doesn't get caught somewhere else. So finally clauses are used just for things that need to happen no matter what in both ordinary and exceptional circumstances, like closing a file if you know that the file was already open. So this method here, print trace stack, this takes advantage of the fact that whenever an exception is thrown, Java takes a snapshot of the stack at the time when that exception was thrown. Let's say took. So Java took a snapshot of the stack. At the moment the exception was thrown, and then later on you can go back and examine that stack trace and see what methods caused the exception, or what methods were on the stack when the exception occurred, and that'll help you debug. Now, the other thing that adds more complexity to all of this is that you can have lines of code inside a catch clause or inside a finally clause that throw exceptions themselves. So what happens then? Well, they get thrown and as normal. So an exception thrown in a catch clause is basically just like an exception thrown in any other piece of code. It just does the usual thing. Wherever you are in the catch clause, the rest of the catch clause doesn't execute. The exception just gets thrown, and you leave down the stack. Yes? The question is, can you nest try and catch clauses inside a catch clause? And the answer is yes, you can. You can nest them inside a finally clause too. So if you had a line of code here that was going to throw an exception, and you didn't want that exception to stop your program, then you could have another try clause inside the catch clause to catch that exception. And you can do the same thing inside of finally. So if an exception gets thrown in a catch clause, and it's not inside a nested try clause, though, then it gets thrown as usual. But I promised you that the finally clause will get executed no matter what, or at least it will start no matter what. So this does not change that guarantee. So the finally clause gets executed first, and then the exception continues its merry way down the stack. And finally, if you have an exception thrown in the finally clause, then now you have two exceptions. You maybe have an exception that you might have already been processing, because maybe an exception got thrown in the try, and then you have to execute this finally code before you carry that exception down the stack, but now you throw in a second exception, and you've got two exceptions. Well, if that happens, then the new exception replaces the old one. This is assuming the new exception doesn't get caught by a nested try clause. So the new exception replaces the old one, and you do not finish all of the finally code if the finally code throws an exception itself. So at this point, the method ends immediately. So a finally clause gives you a guarantee that the code in the finally clause will be started, but it won't necessarily be finished if the finally code throws another exception. Questions about that? Yeah? You have to have a try inside the finally clause if you want to catch an exception in the finally clause. That's the only way. I want to say a quick word about exception constructors. Nothing fancy, but just by convention, most exceptions, most throwables, for that matter, have at least two constructors. One that takes no parameters, and one that takes a string. And generally, this is the way you would write them if you don't want to add anything special of your own. You would just automatically call the superclass constructors for each of these two. But since you want to have both of them, and not just the default one, you need to write out both of them. And so that's the convention. Now, when you construct an exception with a string passed in as a parameter, that string gives you an opportunity to provide an error message that goes along with the exception. And so that error message, there's two ways that it might manifest itself. One is if the exception makes it all of the way out of the main method, then this gets printed as part of your error message. But you don't necessarily have to wait for your program to break. You can catch the exception if you want. And once you've caught the exception, you can read that error message by using the getMessage method. Any questions about that? Dead board. Yeah. Oh, you don't know. It could be either type. So if you call getMessage on one that doesn't have a string, it'll just be an empty string. So the next thing I want to tell you about is something I really want to warn you about. It's called field shadowing. Now, this isn't something to use. It's actually more something to avoid. But since it inevitably happens in some codes when you build really large libraries, it's worth knowing about it. And that's the fact that when you do inheritance, fields can be shadowed in subclasses. So I can have a field called x in the superclass, and then I can declare another field called x in the subclass. So I have two x's in the same object. But it works very differently from overriding. So the way that overriding works, you'll recall, is that the choice of methods is dictated by the dynamic type of the variable that you call the method on. But with field shadowing, fields don't work that way. If you have two different fields with the same name, one in the superclass and one in the subclass, well, the choice of fields is dictated by the static type of the variable that has the two fields with the same name. And so I'll give you an example. Here's a class I'll call super. It will be the superclass. And it has a field and a function. And both of them are basically 2. Question? That's true. In fact, that's going to be the punchline of this section. That's why it's worth warning you about. Yes? I'm making it package just so that there's less writing. So it could be public just as easily, but package works for this. So I'm making it package. So I'm going to have a subclass of that class, which also has a field called x, except this x is 4. I could even change the type if I wanted, but I'll leave it an int, just to make it extra confusing. And I have another function called f that returns 4. And so the x shadows super.x. And the function overrides super.f. And so that's going to be a big difference. I'm going to leave some space here because I'm going to write one more method into the subclass later. You might want to do the same in your notes. So let's write a few lines of code that use these classes. I'm going to declare an object of the subclass. And what does that object look like? Well, it looks like a big box with 2 fields in it named x. And just to distinguish them, I'll call them sub.x and super.x. And I'm going to declare a superclass type static type. And so now I've got 2 variables, sub and sup, which have different dynamic types, but they both point to a superclass object. And I'm going to try several different lines of code and see what comes out. Like I'm going to write I equals sup.x and I equals sub.x. I'm going to ask, after each of these lines of code, what's the value of I? Well, the x that I choose depends on the static type. And the static type of sup is superclass, so that comes out 2. And the static type of sub is subclass, so that comes out 4. But if I want to get my hands on the other x, the one that the variable isn't giving me, it's easy to change that. I just do a cast. So sub is giving me a 4, but if I cast it to a sup and then ask for x, well, then I get a 2. And I can do it the other way around too. I can cast sup to a sub, and again, now because the static type is sub, I get 4. Question? Oh. What am I doing? I am messing up here. Thank you. There. That's what I meant to write. But if you do this with the function f instead of x, like suppose I replace all of these x's with f's. So they're all calling this function f. Then now the choice of function that we call is dictated by the dynamic type, and the object here is a superclass object. So we always call the superclass function, and it always returns 4. We can't call the subclass function on the superclass object at all. Now, you can do this with any variable, but you can also do it with this. Sometimes you'd like to do it with this. So here I'm going to write another function into the subclass called g. Now suppose within the subclass I ask for this dot x. Well, the type of the subclass, well, the static type of this is the subclass, because this is inside the subclass. So I get a 4. And if I want to, I can cast that as well to the supertype. So supertype this dot x. Now I get 2. There's a shorthand that's sometimes useful for this, because this comes up a lot inside of superclasses. You can just write I equals super dot x. And that does the same thing as casting statically to the superclass. So any questions about any of this shadowing so far? Yeah. It works for object types too. You can shadow object types just the way you can shadow an int, but it does not work for functions. Methods are special, unless they're static methods, which is what I'm getting to next. So I want to say again, shadowing is not really useful. Shadowing is mainly a nuisance. But when you're building really large software libraries with lots of components put together, sometimes you can't help using the same name in several different places. So it's worth knowing how to deal with this when it comes up. The other reason it's worth knowing is because, as I just mentioned, static methods follow the same shadowing rules as fields. They do not use the dynamic type. They use the static type. Can anyone tell me why that is? Because they're part of a class and not the object? You mean the static methods? Can you say that again? Well, each object does kind of know what class it is. So it does know about its static methods, just not directly. I mean, so that's not the answer I'm looking for, but yes? Why can't it look at the dynamic type? Okay, well, so here's the reason. When you call a normal method that's not static, you call it with something like x dot method. And so x is a reference to an object, and you can do dynamic method lookup on that reference and figure out what class it points at. And then you look at what class that object is, and that tells you what method to look up. But when you call a static method, there is no object. A static method, you just call it like f of x. You're not calling it on any particular object. And so there is nothing to do dynamic method lookup on. And so the designers of Java didn't have a choice. Even if they wanted to use overriding for static methods, they can't because there's nothing to look up. Yeah. Uh-huh. Well, in a static method, if you're calling the static method from within the same class, then you just write it like that. If you're calling a static method from a different class, then usually you will write the class name in front of it, so that Java knows what class to look in to find that static method. Or like, for instance, math.sign. If you ever want to compute a sign, that's how you do that. But now you're allowed to use an object of a particular class to do this lookup. You can write x.f on a static method if you want to, but usually people don't. And even if you do, Java ignores the identity of x. X is just used to figure out what the right class is. Oh, this is going to use, well, this is a static method here. So it's definitely going to be whatever class you explicitly specify here. Or in the cases like this, in these cases here, if f is a static method, it'll use the static type. So you'll get the same results that we got with the field x. Any other questions about that? So if you find this confusing, it's more important to understand method overriding and not let shadowing poison your thinking. So the shadowing rules are mainly here as a warning when you're working with other people's code where they've done shadowing, which is a regrettable decision. Another bit of Java you should know about is that you can use the final keyword not only for constants to define fields, but you also have final methods and classes. And since you might see these around, I'm going to tell you what they mean. It's very simple. A final method is a method that cannot be overridden. And a final class is a class that cannot be extended. And if you try to override a final method or extend a final class, the compiler just doesn't let you. Now, why would you ever want to declare a method or a class final? The main reason is speed. Sometimes when you have a class that doesn't have any subclasses and doesn't have any interesting superclasses, declaring it final will allow Java to not do dynamic method lookup and just call a method immediately, and that can speed up some of your programs. This is especially true if you have a Java compiler that compilers right down to C instead of to Java bytecode. And this is also true in a lot of C++ compilers as well. So it's a good thing to remember when you learn C++ and need to write really super fast code in that. Any questions about that? Yeah. Hmm. Oh, yes, absolutely. So you can have a method that overrides another method, and the method at the bottom of the chain is final. Like, for instance, you could have a whole hierarchy of subclasses where you have some method f here, some other overriding method here, some other overriding method here, and this one is final, and so you can't have f there. This class is forced to use the same f as this class. It's stuck with whatever it inherits. Other questions? Yeah. Oh, a final field can be shadowed. Any field can be shadowed. Of course. Exactly. Yeah. What's that? Sorry, can you say that slower, please? Uh-huh. Well, it's just that they're completely different ideas. Here the purpose is, this is all about dynamic method lookup. The purpose of final, for these two things, methods and classes, is to save you the cost of dynamic method lookup. Because dynamic method lookup takes time. It's one of the things that makes object-oriented languages sometimes slower than non-object-oriented counterparts. So if you take note of all of the classes that you never plan to make subclasses of, and you declare them final, then your compiler doesn't have to do dynamic method lookup on those, and so it can just call those procedures faster. And so this is something that matters mainly if you really need that last ounce of speed out of your application. Whereas with fields, it's a totally different thing. A final field is just one you're not allowed to change. It's a different concept, same keyword. And finally, I'm not sure this is the right thing to call it. I'll call it the simplified for. I think the Goodrich and Tomassia refer to this as a for each statement. But there's a form of the for statement that's handy sometimes for iterating over the contents of an array. So suppose I have an array, and I want to, oh, question? Enhanced for? Okay. So, all right, so the Java guys at Sun, they call it an enhanced for loop, I guess. What it allows you to do is just iterate through the contents of an array. It's not an index to the array, it's the actual contents. So if I do for int I colon array, then I will take on each of the values in the array in turn. And so if I go ahead and print these out, then this loop is going to print 7, 12, 3, 8, 4, 9. So you'll notice that I'm printing I. I is not iterating from 0 to 5. It's not replacing the for loops that you've been writing to iterate over an array. It's iterating through the actual contents. Now, you're not limited to doing this with ints. You can even do it with objects if you want. So if you have an array of objects, you can do something like, for string s iterates over string array, and then do something to each string in the array of strings. Question? Actually, it works for iterators. So Java has a class called iterator. And what people do is they typically make subclasses of iterator for iterating through their data structures. Like you could have a list iterator that visits each item in your list once, and list iterator would be a subclass of iterator. And then you can just write a for loop that iterates over your list. Now, in order to do this, you have to follow all of the right I'm not sure I've done this right, by the way, because I'm doing this from memory, so I may have botched this. But the idea is that if you follow the procedures for building an iterator, extend all of the right methods, or override all of the right methods with methods that iterate through your kind of list, then you can use any kind of data structure that holds a sequence of items to do these kinds of loops. You just have to follow the protocol. And part of the reason I'm not teaching that protocol is because it uses Java templates, which I'm also not going to teach. Question? Right. So, yeah. So for instance, when this for loop starts off, it constructs a new list iterator. And that list iterator, figures out, whether it's reached the end of the list or not, maybe how long the list is. And then on each iteration, it will call the standard method in your iterator to advance one item in your data structure. Other questions? So one thing about this that I find quirky is the fact that you have to put the declaration right inside the for statement. And the compiler complains if you don't. Like if you try writing int I and then for I going through the array, the compiler doesn't like that. The compiler barfs on that. You have to actually declare your iterator right here. Any more questions on that? All right, well, on Friday we will learn how to program a computer to play tic-tac-toe.